Introduction, The Infinite Quest. We'll begin with humanity's timeless fascination with the cosmos. Since the earliest days, people have looked to the stars, wondering what lies beyond. This journey has driven centuries of exploration, scientific revolution, and discovery. Today, we continue that legacy, not only with telescopes and spacecraft but with complex theories and simulations. Throughout this lecture, we'll answer questions like, how did the universe begin? How does it work? And what might its ultimate fate be? The origins of the universe. To understand the cosmos, we start at its beginning, at least as far back as our knowledge allows. The Big Bang theory serves as the foundation of cosmology. Imagine a singularity, a point of infinite density, exploding outward. But what came before, and how did we arrive at this theory? Through observations of cosmic microwave background radiation and the redshift of galaxies, we gain insight into the rapid expansion of the universe. Yet, mysteries remain. Did the universe emerge from nothing, or was there something before? Next, we'll move on to the early stages following the Big Bang, a period of rapid cooling where subatomic particles formed atoms, giving rise to the first elements. This process set the stage for the emergence of stars and galaxies. Mapping the structure of the universe. As the universe expanded, matter began organizing itself in a vast, intricate structure. Think of it as a cosmic web, filled with galaxies, clusters, and voids. Galaxies are not randomly scattered, instead, they form clusters bound by gravity. What holds this structure together? Here, we introduce dark matter, a mysterious substance we can't see but infer through gravitational effects. Alongside dark matter is dark energy, a force driving the accelerated expansion of the universe. These two components, though unseen, dominate our cosmos, guiding its shape and evolution. Our solar system. Coming closer to home, our solar system provides a microcosm of cosmic diversity. Born from a collapsing molecular cloud, our Sun formed at the center, surrounded by a rotating disk of gas and dust. Over time, this disk coalesced into planets, moons, asteroids, and comets. We'll examine each planet's unique characteristics, from the scorching surface of Mercury to the icy rings of Saturn. Additionally, some moons like Europa and Titan are of special interest due to the potential for subsurface oceans, raising the exciting possibility of extraterrestrial life. The life cycle of stars. Stars are the building blocks of galaxies and life itself, forging elements in their cores. We'll explore how stars form in nurseries of gas and dust, igniting with nuclear fusion to shine brightly. As they age, stars undergo transformations, swelling into red giants or exploding in spectacular supernovae. These violent ends produce neutron stars and black holes. Black holes, with their intense gravitational fields, pull everything, even light, into an unseen abyss. Understanding black holes challenges our grasp of physics, as they reveal extreme warps in spacetime. Spacetime and relativity. Speaking of spacetime, this concept is crucial to understanding the universe. According to Einstein's theory of general relativity, massive objects warp the fabric of spacetime, creating what we perceive as gravity. We'll discuss how this warping allows objects to orbit stars, but also how it distorts time itself. For instance, time slows near massive objects, a phenomenon known as time dilation. This effect has practical implications. It's taken into account in the GPS satellites orbiting Earth. Near black holes, time stretches dramatically, hinting at possibilities like time travel, albeit theoretical. Exoplanets and the search for life. Beyond our solar system, thousands of exoplanets orbit other stars. Some are gas giants like Jupiter, others are rocky and Earth-like. The search for exoplanets in the habitable zone, where conditions might allow liquid water, is at the heart of the quest to find life. Our understanding of habitability comes partly from studying extremophiles on Earth, organisms that thrive in extreme environments. If life can survive near hydrothermal vents or in acidic lakes, perhaps similar life forms exist on distant planets with similar harsh conditions. The future of space exploration. Looking ahead, we stand on the brink of a new era in space exploration. Manned missions to Mars, lunar bases, and even potential space colonies are now within the realm of possibility. This vision is powered by advancements in rocket technology and the rise of private space companies like SpaceX and Blue Origin. By reducing launch costs and increasing accessibility, these companies are expanding our potential to become a multiplanetary species. We'll examine the challenges of long-term space travel, from radiation exposure to psychological effects, and the solutions being proposed. The fate of the universe. With a grasp on the past and present, we turn to the future, pondering the universe's ultimate fate. Cosmologists propose scenarios like the Big Rip, where dark energy tears everything apart, or the Big Crunch, a collapse back into a singularity. We'll also touch on the multiverse theory, which suggests our universe is but one of many. Though speculative, these ideas broaden our understanding and invite us to ponder the true scale of existence. Conclusion: our place in the cosmos. After exploring such vast and varied topics, we're left with a humbling realization: in the grand scale of the universe, we are but a small part. Yet, our curiosity and drive to understand elevate us. As we look out into space, we also reflect inward, gaining insight into who we are and what it means to be a part of this magnificent cosmos. Delving into the Big Bang and the early universe. As we investigate the Big Bang, let's discuss how scientists measure the early moments of the universe. Observations from telescopes like the Hubble and, more recently, the James Webb Space Telescope, provide incredible details. These telescopes allow us to look back in time by capturing light that has traveled billions of years. The Big Bang timeline. Within fractions of a second after the Big Bang, the universe was a hot, dense plasma. We move into the inflationary period, a time when the universe expanded exponentially faster than the speed of light. This phase laid the foundations for everything that followed, and recent theories suggest that quantum fluctuations during inflation led to variations in density that would eventually form galaxies. Formation of fundamental forces. During this early phase, the four fundamental forces, gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, began to separate. This unification and later separation of forces is one of the unsolved mysteries in physics, with researchers working to understand how these forces interacted at high energy levels. Cosmic structure and the role of dark matter. With the universe cooling down, particles began clumping together, guided by gravity. This led to the formation of gas clouds that would become stars. Yet, even as we study the formation of galaxies, we're left with questions. Observations reveal that galaxies rotate too quickly for the visible mass to hold them together, a phenomenon that led to the discovery of dark matter. Dark matter as a gravitational framework. Dark matter, although invisible, provides a gravitational scaffold around which galaxies cluster. Various detectors on Earth, such as those buried deep underground or in space, aim to capture evidence of dark matter particles. Yet, despite these efforts, the exact nature of dark matter remains elusive. This introduces students to the concept of scientific inquiry where not every answer is clear, highlighting the frontiers of modern astrophysics. Dark energy and cosmic expansion. Then there's dark energy, a mysterious force causing the universe to expand at an accelerated rate. It's as if the universe is being pulled apart by an unknown force, leading to questions about its long-term effects. Will galaxies drift so far apart that night skies become empty? Will atoms themselves be ripped apart? Here we touch on different theories about dark energy, exploring potential explanations like the cosmological constant or new, undiscovered particles. Exploring our solar system's unique features. Moving to the solar system, each planet has its unique story. Understanding the solar system isn't just about knowing what each planet is made of but also uncovering the processes that shape them. For example, Mercury with its extreme temperature differences offers insights into planetary evolution. Venus serves as a case study in runaway greenhouse effects, which is relevant to Earth's climate discussions. Mars tantalizes us with evidence of past rivers and lakes, raising the question of whether it once harbored life. The gas giants and beyond. Our gas giants, Jupiter and Saturn, act as guardians of the inner planets, their immense gravity pulling in comets and asteroids that might otherwise hit Earth. Each giant planet has a fascinating atmosphere and a collection of moons, some of which, like Europa and Enceladus, show signs of subsurface oceans. These moons may contain hydrothermal vents, environments similar to those on Earth where life thrives in complete darkness, raising the exciting prospect of alien microbial life. The evolutionary path of stars and the formation of black holes. The life cycle of stars is a cosmic drama on a scale beyond human comprehension. Starting from stellar nurseries, stars ignite as nuclear fusion kicks in, converting hydrogen into helium. This fusion creates the light and heat that eventually enables life on planets. Stellar deaths, supernovae and black holes. Massive stars meet a violent end. Once they exhaust their nuclear fuel, they collapse under their own gravity, leading to supernova explosions. The remnants of these explosions can form neutron stars or, if massive enough, black holes. In a black hole, gravity is so intense that it warps space and time, creating an event horizon, the point beyond which nothing can escape. Black holes challenge our understanding of physics, merging concepts from quantum mechanics and general relativity. They also give rise to the idea of gravitational waves, ripples in spacetime detected by observatories like LIGO, which capture cosmic events as they unfold across the universe. Spacetime, relativity, and the cosmic playground. Einstein's theories of special and general relativity transformed our understanding of space and time, unifying them into a single, four-dimensional fabric. In our daily lives, we rarely notice relativity, but on a cosmic scale, it's fundamental. Time dilation and the twin paradox. Let's consider time dilation, a phenomenon where time moves slower for objects in motion or in strong gravitational fields. The twin paradox is a famous thought experiment that illustrates this. One twin travels near the speed of light while the other stays on Earth. Upon returning, the traveling twin is younger, showcasing how time flows differently under certain conditions. The warping of spacetime and gravitational lensing. Another consequence of relativity is gravitational lensing. Massive objects like galaxies or black holes can bend light, acting like cosmic lenses that reveal objects hidden behind them. This phenomenon has allowed astronomers to detect distant galaxies and study the distribution of dark matter. Exoplanets and the quest for extraterrestrial life. The discovery of exoplanets has revolutionized our understanding of planetary systems. Using methods like the transit method, where a planet passes in front of its star, dimming its light, and radial velocity, where a star wobbles due to a planet's gravity, astronomers have catalogued thousands of worlds. Some of these planets are in the habitable zone, where temperatures might allow for liquid water. Signs of life and the study of biosignatures. One major focus is detecting biosignatures, chemical markers like oxygen or methane that may indicate life. Advanced telescopes aim to analyze exoplanet atmospheres, searching for these clues. We also explore astrobiology, a field that studies life in extreme environments on Earth to understand the conditions under which life might thrive elsewhere. Human exploration and the expansion of our reach. Human exploration is not just a technological feat, it's a testament to human curiosity. As we plan missions to Mars and consider colonizing space, we encounter profound ethical and logistical challenges. The Mars Challenge. Mars, though close, poses significant hurdles: radiation exposure, low gravity, and psychological isolation. Researchers are working on solutions like artificial habitats, radiation shielding, and advanced life support systems. A mission to Mars could pave the way for longer journeys into the solar system and beyond. The Moon as a stepping stone. returning to the Moon offers a practical training ground. Lunar bases could support Mars missions, acting as supply hubs and research stations. The Moon's resources, like water ice, could provide fuel for spacecraft, making it an essential part of our interplanetary future. The ultimate fate of the universe and the multiverse hypothesis. After exploring all that exists within our universe, we turn to questions of its end. Cosmologists debate various scenarios: the Big Rip, where galaxies are torn apart as dark energy accelerates, the Big Crunch, a potential collapse into another singularity, or the Big Freeze, where stars burn out, leaving a cold, dark universe. Multiverse theories and quantum mechanics. Finally, we arrive at one of the most speculative yet fascinating topics, the multiverse hypothesis. Some physicists suggest our universe is one of many, each with different physical laws. These ideas challenge our understanding of reality and hint at endless possibilities, sparking philosophical questions about the nature of existence itself. Closing reflection: the human drive to explore. In the end, space exploration is not just about what we discover, it's about how these discoveries change us. As we probe the cosmos, we're also exploring the limits of our knowledge and resilience. Through science, we uncover mysteries that deepen our understanding of life, purpose, and the human spirit. Diving into quantum fluctuations and the inflationary epoch. One of the most mind-bending aspects of the Big Bang Theory is how quantum mechanics comes into play in the earliest fractions of a second. During the inflationary epoch, quantum fluctuations, tiny random variations in energy levels, created small differences in density throughout the universe. These fluctuations, though minuscule, were essential. They became the seeds around which galaxies and clusters would later form. The role of particle physics in the early universe. In those first moments, temperatures were so high that particles like quarks and gluons moved freely, forming a primordial soup. As the universe cooled, these particles combined to form protons and neutrons. This process, known as baryogenesis, allowed matter to come together, setting the stage for elements to form. Theories like grand unified theories, GUTS, aim to explain how the forces we observe today split from a single force, revealing the fundamental unity of nature. Dark matter and dark energy, the invisible forces shaping everything. Dark matter and dark energy remain two of the greatest mysteries in physics. Dark matter doesn't interact with light or electromagnetic forces, making it invisible to us. Yet its gravitational pull is unmistakable, influencing the rotation of galaxies and the motion of galaxy clusters. Searching for dark matter. Scientists have developed several experimental methods to detect dark matter, including direct detection experiments using ultrasensitive detectors in underground labs to capture rare interactions between dark matter particles and ordinary matter. Others pursue indirect detection by searching for cosmic rays or gamma rays produced when dark matter particles might collide and annihilate each other. The Large Hadron Collider, LHC, also probes for new particles that could comprise dark matter, a quest that pushes our understanding of the standard model of particle physics. Dark energy and the accelerating universe. Dark energy's influence on the universe's expansion was first observed in the late 1990s when scientists noticed that distant supernovae were dimmer than expected, indicating they were farther away than predicted. This discovery led to the theory that some unknown force, dark energy, was pushing galaxies apart, accelerating the universe's expansion. While it comprises nearly 70% of the universe, we know almost nothing about its nature. Some theorists suggest dark energy could result from a new, undiscovered field, while others speculate that it might be a property of space itself. The mysteries of planetary formation and habitability in our solar system. Studying the formation of planets in our own solar system provides a blueprint for understanding exoplanets around other stars. Our solar system's history is marked by chaotic processes, such as planetary migration. For example, Jupiter's migration likely played a role in shaping the asteroid belt and may have even influenced the development of life on Earth by redirecting comet and asteroid impacts. Mars, a case study in planetary evolution. Mars holds particular interest because it shows signs of once having liquid water, a crucial ingredient for life as we know it. Ancient riverbeds, lakebeds, and evidence of past volcanism tell a story of a warmer, wetter Mars billions of years ago. Understanding what happened to Mars's atmosphere and climate could reveal insights into planetary climate change and stability, which are essential for understanding habitability. The outer solar system and icy moons. The outer solar system contains a wealth of icy moons with potential subsurface oceans, such as Europa and Enceladus. These moons have become prime targets for astrobiology missions because they offer the possibility of harboring life in environments isolated from the harsh conditions of space. Scientists believe that tidal forces from their parent planets may create enough heat to keep these oceans in a liquid state, creating environments similar to Earth's deep-sea hydrothermal vents where life thrives without sunlight. The formation and evolution of black holes and neutron stars. Massive stars that end their lives in supernova explosions create some of the most extreme objects in the universe, black holes and neutron stars. Neutron stars are incredibly dense, with a teaspoon of neutron star material weighing as much as a mountain. Types of black holes and their formation. Black holes come in different sizes, from stellar mass black holes formed by collapsing stars to supermassive black holes found at galaxy centers. These supermassive black holes can contain millions to billions of times the mass of our Sun. How they formed remains a mystery. Did they grow from smaller black holes, or did they form directly from massive clouds of gas early in the universe? The event horizon and singularities. A black hole's event horizon marks the point beyond which nothing, not even light, can escape. Inside, matter is crushed into a singularity, where our current understanding of physics breaks down. This leads to intriguing questions. Does a singularity represent a true edge of the universe, or are there hidden dimensions and other unknown properties we have yet to understand? These mysteries lead us into the realm of theoretical physics, where string theory and quantum gravity aim to provide answers. Expanding on space-time, gravitational waves, and time travel. Einstein's theories of relativity not only describe gravity but have also opened up new fields of inquiry, such as gravitational waves and the possibility of time travel. Gravitational waves, a new era in astronomy. In 2015, the LIGO experiment detected gravitational waves for the first time, confirming a prediction Einstein made a century earlier. Gravitational waves are ripples in spacetime caused by cataclysmic events, like the collision of black holes. These waves allow us to observe the universe in a new way, providing insights into events that are otherwise invisible. Through gravitational wave astronomy, we can study objects and phenomena in the distant universe, from neutron star collisions to black hole mergers. Time travel and wormholes. General relativity also introduces the concept of wormholes, hypothetical passages through spacetime that could create shortcuts between distant regions of the universe. While purely theoretical, wormholes offer the tantalizing possibility of time travel. Some physicists suggest that under certain conditions, a wormhole could allow an object to travel back and forth in time. While the energy and stability requirements are currently far beyond our reach, the idea of wormholes fuels both scientific curiosity and science fiction. The astrobiological potential of exoplanets and biosignature detection. Our galaxy alone contains an estimated 100 billion stars, many of which have planetary systems. Some of these planets orbit within the Goldilocks zone, where temperatures could support liquid water. Atmospheric analysis and the search for biosignatures. With advancements in spectroscopy, we can analyze exoplanet atmospheres for biosignatures, chemical compounds like oxygen, ozone, or methane that might indicate biological activity. Missions such as the James Webb Space Telescope and upcoming projects like the European Extremely Large Telescope aim to characterize the atmospheres of rocky exoplanets, focusing on those that might resemble Earth. Expanding definitions of habitability. As we study extremophiles on Earth, organisms thriving in places once thought uninhabitable, like acidic lakes and deep-sea vents, we broaden our understanding of what conditions life might adapt to. This raises exciting possibilities for life in the harsh environments of other planets and moons, challenging the notion that liquid water and moderate temperatures are strict requirements. The logistics and ethics of human exploration beyond Earth. As we prepare for potential manned missions to Mars, we face numerous challenges. The psychological effects of isolation, radiation protection, and sustainable life support systems are all critical areas of research. Ethical considerations and planetary protection. Planetary protection involves preventing contamination of other planets with Earth-based organisms, as well as protecting Earth from any potential biohazards brought back from space. This consideration is particularly important as we begin exploring icy moons and Mars, where the possibility of discovering microbial life is higher. Speculative physics and the multiverse. The ultimate fate of the universe could unfold in several ways. According to current theories, the universe may either expand forever, rip itself apart, or collapse back on itself. But what if our universe is just one of many? The many worlds of quantum mechanics. The many worlds interpretation of quantum mechanics proposes that every possible outcome of a quantum event actually occurs in a separate, branching universe. This theory offers a mind-bending view where countless versions of reality coexist, each branching out from every decision and event. If true, this would mean that our universe is just one of an infinite number of parallel realities, each with different versions of you and me. Closing reflections, humanity's role in the cosmos. As we push the boundaries of science and technology, we must also contemplate our role as cosmic explorers. Are we alone in the universe? Are we on the cusp of becoming a multiplanetary species? And as we look outward, we also turn inward, asking timeless questions about purpose, connection, and the legacy we will leave behind. Unresolved questions in the Big Bang and early universe. As we discuss the origins of the universe, we confront the question of what came before the Big Bang, if anything. Loop quantum gravity and string theory are two leading attempts to reconcile general relativity and quantum mechanics, both proposing radically different ideas of spacetime at the smallest scales. According to loop quantum cosmology, spacetime itself is made of discrete loops, which could mean the universe has cycles of expansion and contraction, hinting at a bounce rather than a singular Big Bang. This opens the door to the idea of a universe that is both eternal and cyclical, constantly regenerating in a vast cosmic dance. The multiverse and eternal inflation. In the concept of eternal inflation, our universe is one bubble in an endlessly expanding cosmic foam, with other universes potentially having completely different physical laws and constants. This raises fascinating philosophical and scientific questions. Is our universe fine-tuned for life by coincidence, or does the multiverse suggest that life could emerge in any of these bubbles under the right conditions? Eternal inflation theory thus offers a vast canvas for understanding existence itself, challenging our assumptions about reality. Dark matter and alternative theories of gravity. Despite decades of research, dark matter remains undetected, leading some scientists to propose alternatives to dark matter itself. Modified Newtonian dynamics, MOND, for example, adjusts the laws of gravity at extremely low accelerations, which could explain galaxy rotation curves without dark matter. Emergent gravity and tensor vector scalar, TeVis, theory also aim to solve the dark matter puzzle by suggesting modifications to general relativity on cosmic scales. These theories challenge the very structure of Einstein's ideas, offering potentially radical shifts in our understanding of gravity and motion. Axions and supersymmetry as dark matter candidates. Within particle physics, axions are hypothetical particles that could explain dark matter's behavior. Unlike particles in the Standard Model, axions interact very weakly with matter, which makes them difficult to detect but an intriguing candidate for dark matter. Supersymmetry also suggests particles like the neutralino could account for dark matter. These particles, predicted in theoretical physics but not yet observed, offer paths for further exploration into the nature of dark matter and its role in shaping the universe. Comparative planetology and the search for Earth's twin. As we study exoplanets, we also learn more about our own solar system's unique features. Comparative planetology, the study of planets as a group rather than individually, reveals that planetary systems come in a variety of configurations, and that Earth-like conditions might be rare or even unique. Some systems contain super-Earths, planets larger than Earth but smaller than Neptune, while others lack gas giants like Jupiter, which protect Earth by deflecting incoming comets and asteroids. The study of these varied systems enhances our understanding of planet formation and the specific conditions necessary for habitability. The search for Planet 9 and Kuiper Belt mysteries. In recent years, evidence has emerged suggesting a mysterious, massive object, often referred to as Planet 9, lurking on the edges of our solar system. Based on the unusual orbits of distant objects in the Kuiper Belt, Planet 9 might be a super-Earth or even an escaped planet captured by the Sun's gravity. Its discovery would redefine our understanding of the solar system's formation and dynamics, and even hint at the possibility of other, yet unseen planets or objects influencing our system from afar. The physics of neutron stars and black holes. Neutron stars are laboratories for extreme physics. Their matter is compressed so densely that atomic nuclei are crushed together, creating a state of matter we can't replicate on Earth. Quark stars, even more exotic objects that may exist at an even greater density, are theorized to form if neutrons break down into quarks. This would create a strange, almost theoretical state of matter. Gravitational waves as tools to study black holes. Since the discovery of gravitational waves, scientists have used them to observe black holes and neutron star collisions. These waves provide insight into objects that don't emit light, opening a new realm of multi-messenger astronomy, where we observe cosmic phenomena with light, gravitational waves, and even neutrinos. For instance, the observation of a neutron star collision not only produced gravitational waves but also emitted heavy elements like gold and platinum, illustrating how elements essential to our world were forged in cosmic cataclysms. Primordial black holes and dark matter. Primordial black holes, theorized to have formed shortly after the Big Bang, are another candidate for dark matter. If these small, ancient black holes exist, they could contribute to dark matter and help explain some of its gravitational effects. Detecting these primordial black holes would be a breakthrough in understanding both dark matter and the early universe, potentially bridging cosmology and particle physics. The quantum foundations of spacetime and gravity. In attempting to merge quantum mechanics and general relativity, physicists explore ideas like quantum foam, a hypothetical state where spacetime itself becomes unstable at the smallest scales. If true, this would mean spacetime fluctuates at incredibly tiny scales, creating a foamy structure with unpredictable properties. Entanglement and the fabric of the universe. Quantum entanglement, a phenomenon where particles remain interconnected regardless of distance, has led to theories about how spacetime itself might emerge from these connections. Some physicists propose that the fabric of the universe could be woven from quantum entanglement, with spacetime as a byproduct. This view of spacetime as an emergent phenomenon challenges our conventional understanding and introduces the idea that consciousness, physics, and reality might be interconnected on a fundamental level. The holographic principle. The holographic principle suggests that all the information contained in a region of space can be described by data encoded on the boundary of that region, much like a hologram. This idea, rooted in black hole physics and string theory, implies that our three-dimensional reality might be a projection of information encoded on a distant, two-dimensional surface. It's a concept that challenges not only physics but also philosophy, prompting questions about the nature of reality itself. Chapter 6, Exploring New Definitions of Habitability. As we continue our search for life, the concept of habitability expands. Planets with subsurface oceans, like Europa, or those with dense atmospheres, like Venus, challenge our traditional idea of a habitable zone. Life might arise under ice sheets, near hydrothermal vents, or even in clouds, as speculative research on Venus's upper atmosphere suggests. The role of artificial intelligence in exoplanet research. AI has become essential in analyzing vast data sets from telescopes like Kepler and TESS, which observe thousands of stars simultaneously. Machine learning algorithms can detect subtle signals, helping us find smaller, potentially Earth-like planets and even identify potential biosignatures. As AI evolves, it may become crucial in distinguishing genuine life signature signals from noise, accelerating the search for extraterrestrial life. The Panspermia hypothesis and interstellar life. The Panspermia hypothesis suggests that life might travel between planets or even star systems, spreading microbial organisms via asteroids, comets, or cosmic dust. If true, this would imply that life on Earth, and potentially elsewhere, originated from beyond our planet, making life a cosmic phenomenon. Studying the resilience of extremophiles offers clues about life's ability to survive space travel, bringing new meaning to the idea of universal life. Mars colonization and ethical challenges in space. With plans to colonize Mars, we face unprecedented ethical and practical questions. The presence of human settlers could introduce Earth-based microorganisms to Mars, potentially contaminating any native ecosystems that may exist. We must weigh the benefits of exploration with the responsibility to preserve other worlds as they are, respecting their unique histories. Terraforming and the long-term survival of humanity. Terraforming, the idea of transforming Mars's climate to make it more Earth-like, involves complex methods like releasing greenhouse gases to warm the atmosphere. But is it ethical, or even practical, to alter an entire planet? Some argue that humans should adapt to Mars rather than changing Mars to suit human needs. This debate touches on deep questions about humanity's role as stewards of life and ecosystems. New frontiers in cosmology and beyond. As we reach the limits of observable space, we're left with tantalizing possibilities. Could there be universes with entirely different laws of physics, inaccessible to us yet influencing our universe in subtle ways? The anthropic principle and fine-tuning. The anthropic principle suggests that the universe's fundamental constants appear fine-tuned for life. Some scientists argue this fine-tuning implies purpose, while others see it as a selection effect. If the universe weren't suitable for life, we wouldn't be here to observe it. The anthropic principle straddles science and philosophy, leading us to ask whether there's a greater design or if life is simply a cosmic accident. Future of physics, unifying the laws of nature. The search for a theory of everything aims to unify general relativity with quantum mechanics, creating a single framework that describes all forces and particles. Such a theory could reveal hidden dimensions, new particles, or even the origins of dark matter.